Today we're going to open a new chapter and we're going to explore frequency modulation. And with a little luck, I'll show a demonstration of frequency modulation using the GNU Radio companion. As we always do, let's start with our communications model. There's the microphone. Let that microphone be followed by a filter. We'll let that filter have a band pass of 300 to about 3000 Hertz. Let the output of the filter enter the modulator. Perhaps boost the signal with an amplifier and then go to the broadcast antenna. So far, it's the same thing that we've done with our AM systems. But this is not AM. This is now FM. Inside the modulator, there's a device called the voltage-controlled oscillator. Remember, with AM, it was a fixed oscillator, right? We called it the local oscillator. Well, this is similar, except now the local oscillator is variable. So it can be changed. The output frequency can be changed by changing the voltage. While we're here, we should tidy this up a little bit. This entire block is the transmitter. In fact, we'll call it a FM transmitter. To understand this VCO, let's jump over to our GNU Radio companion. In the center of the flow graph, we find the VCO. It has an adder attached to it. That adder has a sinusoid generator, and it also has a constant source generator. If we open this up, we see that the constant source is called the carrier, which is in kilohertz. And then our signal source here, we're going to call that the intelligence with a frequency in hertz. Both of these output a voltage. The adder simply adds them together. We have an audio sync, which will allow us to hear the output. And there's a GUI sync, which will allow us to see things in the frequency and time domain. Go ahead and start the flow graph. There's the tone. Let me mute that for now, though. These sliders up above allow us to change the frequency to anything we desire. So to get started, let's set the carrier to 5 kilohertz. If we zoom in on the spectrum, we see the carrier at 5 kilohertz. If you're curious, it sounds like this. Right, that's fairly annoying. The intelligence up here can be changed, as can the amplitude of the intelligence. Now remember, a voltage-controlled oscillator is controlled by the voltage. So by feeding it a sine wave of different amplitudes, we would expect this carrier to move. So let's start out with something really simple. We'll set this to be quite slow, 0.1 hertz, and we'll add some amplitude. And you should see this tone sliding back and forth. And if I turn the sound on, I think you can see what's going on, or hear what's going on a little better. All right, quite annoying. But you can see that the frequency is indeed changing. And if we speed it up a little bit, so maybe double the speed, it should go back and forth a little bit faster. And if we listen to the sound, it should be perhaps a little more annoying. Oh, lovely. Okay, let's go back to the drawing board and see if we can make some sense of this. The operation of this VCO can be described graphically. On the input axis, we have the input voltage. After all, it is a voltage-controlled oscillator. On this axis, we have frequency deviation. And there is a linear relationship between the two. As the input voltage is changed, which is to say we slide this way or that way, the frequency will deviate from its original point. Cover your ears because we're going to turn on that annoying sound again. You can hear the frequency changing as it goes up and down. Right? It's going up and down, so very annoying. The reason it's doing that is because the input voltage is going up and down, which means the output frequency of the oscillator is determined by the input voltage. Again, VCO. If we were to put numbers on this, we would call our carrier 5 kilohertz. That is the frequency that we idle at if there is no modulation. Right? There's a single carrier at 5 kilohertz. As we start to add input voltage, we move in the horizontal, which means the output frequency might go up to, perhaps this point here, or maybe down to this point here. Let this be 1 volt. Let this be negative 1 volts. And our frequency might go up to 6 kilohertz or down to 4 kilohertz. Looking back at this diagram, we would describe this as the modulating frequency, F sub m, not to be confused with FM, mind you, but the modulating frequency, and there's a voltage associated with it. The changing in that voltage changes the output frequency of the oscillator, which is then amplified and then broadcast. When we consider this graphical description, we could talk about the voltage of the modulating frequency, not the frequency, but the voltage associated with the microphone, and the frequency of output. If we have no voltage going in, the output frequency of the transmitter would be 5 kilohertz. If 1 volt goes in, the frequency might increase to 6 kilohertz, and if negative 1 volt goes in, this will drop to 4 kilohertz. And you hear that as a tone. Were we to sketch this in the time domain, we could describe a 5 kilohertz signal that would look like this. Sometime later, we might describe a 6 kilohertz signal. You can see the frequency is higher, but the amplitude is the same. Then sometime later, we might have the 4 kilohertz signal. So voltage in equals 0, voltage in equals 1, and voltage in equals negative 1. Frequency out is equal to 5 kilohertz, 6 kilohertz, and 4 kilohertz. In each case, you'll notice that the output amplitude remains constant. In the time domain, using an oscilloscope, if you were to look at the FM signal, you would see there is always a constant amplitude. Here's a new and related term for you. It's known as the modulation index. That's a term that should be familiar to you. You encountered it with AM modulation, where the modulation index was some voltage max minus a voltage min all over Vmax plus Vmin. And in that particular case, we talked about the envelope of an AM transmitter output, where the carrier rode inside here, contained within the envelope. This was the voltage min, and this was the voltage max. So keep in mind, that's the modulation index for AM. For FM, the modulation index, M sub F, is described as the frequency deviation divided by the modulating frequency. Here, frequency deviation is a question of how much the pitch changed. As the transmitter changes output frequency, what is this upper number and what is this lower number? The modulating frequency asks how fast the tone is changing. For that, we have to go way back up to our original diagram. If you are at the bottom of the voice frequency, the modulating frequency is changing at a rate of 300 Hertz. At the top of the voice frequencies, the modulating frequency is changing at a rate of 3000 Hertz. A typical example would look something like this. The problem would identify an FM transmitter. In this particular case, we'll let the deviation be 12 kilohertz. Finally, the modulating frequency is identified as 4 kilohertz. We're given two of the three parameters. The modulation index is equal to the frequency deviation over the modulating frequency. In this case, that's 12 kilohertz over 4 kilohertz, giving us a modulation index of 3. Actually, we should go back and make a little modification to this. When we're talking about the frequency deviation, we're actually concerned about the maximum frequency deviation. When we're concerned about the modulating frequency, we're concerned about the maximum modulating frequency. Keep in mind that this is the baseband intelligence. It's our voice signal. So if we go back to our original communications model, we are much more interested in what the limit is. What is the highest frequency we're going to pass on to the modulator? That's a concept that should raise some alarm bells. And if you're tracking, I think you know where we're going to go next. In the AM transmitter, bandwidth was described as 2 times the maximum modulating frequency. Assuming a voice frequency, the modulating frequency, the maximum modulating frequency, would equal 3000. The bandwidth is therefore 2 times 3 kilohertz, giving a total AM modulator bandwidth of 6 kilohertz. In the frequency domain, we sketch that as the carrier, so this is the frequency of the carrier, and then 2 sidebands. So this is FC plus the modulating frequency, and this is the frequency of the carrier minus the frequency of the modulating signal. And we call this the upper sideband and this the lower sideband. Keep this picture of AM modulation in your mind, as you'll find FM shares many of the same attributes, which we're going to shift back to GNU Radio and explore what those are. I've reset the numbers such that we have a 5 kilohertz carrier. You can see that very clearly here. Let's set the intelligence frequency. You can think of that as the voice frequency coming in to 100 hertz. And now we're going to increase the amplitude. We're going to talk louder into the microphone. It's one way of looking at that. So here goes. Immediately, you'll see that this is not AM. FM has multiple sidebands. This is still the carrier. You can see that at 5 kilohertz. The first sideband appears at 5.1 kilohertz, which is the summation of our carrier, which was 5 kilohertz, and that 100 hertz signal. This is the negative of that sideband, so 4.9. So you would call this one and this one the first sideband pair. There's a second sideband pair here at 5.2 and 4.8. So you could talk about this being the carrier, this being FC plus FM. This sideband is FC plus 2 FM, and this one FC plus 3 FM. So there's the frequency of the carrier. Remember, it was a 5 kilohertz. The frequency of our modulating signal is 100. So 5,000 plus 3 times 100 is 5.3K. And of course, there is a negative sideband complement over here as well at 4.7. As we increase the amplitude of the intelligence, we see that there are more sidebands created. So the bandwidth of an FM transmission just keeps getting wider and wider the louder you speak into the microphone. At this point, our bandwidth is actually 1 kilohertz. So here's your F2 minus F1. That's 1 kilohertz, which means there are 5 sideband pairs. 1, 2, 3, 4, 5. But we can keep going. And what I want to do is I want to show you a few special points on this graph. This is one of them. You'll see that the amplitude of the carrier is the same as the first sideband pair. As we continue increasing the amplitude, you'll notice that the carrier is starting to dip. Keep in mind that this is a logarithmic scale, so that carrier has been reduced by about 40 dB, which is quite significant. In an ideal situation, the carrier actually goes to 0, which is kind of a fascinating result. Continuing on, there are a few other interesting points. So the carrier comes back up, and now you see the first sideband pair. The first sideband pair is going to 0. And we could continue on with that, ever increasing the bandwidth and watching these individual sideband pairs increasing and then decreasing in amplitude. As always, we're concerned about the bandwidth of the transmissions. One of the questions you might be asked is, what is the bandwidth given the number of sideband pairs and the modulating frequency? In this particular example, there are 11 sideband pairs. So here's the carrier. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th. So 11 sidebands in the upper side and 11 in the lower side. Given that the modulating frequency is 100, we can say that 11 times 100 would be the distance from here to here, so that's 1.1K. But don't forget the lower sideband, so the total bandwidth here is 2.2 kilohertz. Back to the drawing board. In the frequency domain, we have the carrier, the first sideband pair at FC plus the modulating frequency and FC minus the modulating frequency. And that should look familiar. That's what we had in AM. But with FM, we add additional sideband pairs. So FC plus 2 by the modulating frequency Fc minus 2 by the modulating frequency. And we can continue on for as many sideband pairs as we have. In our example, this was 5 kilohertz. The first sideband pairs occurred at 5.1 kilohertz and 4.9 kilohertz. And I'll leave it to you to fill in the rest of these frequencies. Let's add a new equation to our note cards. Bandwidth is equal to 2 by the modulating frequency by the number of sideband pairs. This is the example I just did with the GNU radio. We talked about the bandwidth is 2 by the modulating frequency, which was 100 hertz. And I believe we had 11 sideband pairs. So our bandwidth was 2.2 kilohertz. All of this is starting to look like a most excellent problem for an exam. The only piece that's missing is the amplitude of the carrier and of the sideband pairs. This might look like an impossible problem, but if you know the modulation index, you can consult a table of Bessel functions which will tell you exactly what these relative amplitudes are. This is a graph of those Bessel functions. On the horizontal axis is the modulation index. On the vertical axis is the relative amplitude of the carrier and sideband pairs. This line in red represents the carrier. The line in green, that's this one here, represents the first sideband pair. This line in blue represents the second sideband pair. So carrier, first sideband pair, second sideband pair. This is a good time to consult your textbook, where you'll see that there are additional sideband pairs. But for simplicity, I thought this was a good representation. You'll also find the data in tabular form, which might make things a little bit easier. What I'd like to do now is show you some of the special points on the Bessel functions. Let's take the condition where the modulation index is 0, and we find the carrier to be at the maximum amplitude. What we've just described is an unmodulated carrier. You see the intelligence amplitude is turned down to 0, and all that remains is the carrier. By the way, you do see some small sidebands here, but look at the amplitude. They're almost 100 dB down, so they're, for all intents and purposes, non-existent. The next point of interest occurs when the carrier has the same amplitude as the first sideband pair. That appears to happen when the modulation index is about 1.5. We can find that point by increasing the amplitude of the intelligence until the carrier and the first sideband pairs match. The next point of interest occurs when the carrier dips to 0, which occurs at a modulation index of 2.41. We increase the amplitude of the intelligence and continue to do so until the carrier dips to 0. Keeping in mind that this is a dB scale, that carrier is very much reduced. Before I forget, go ahead, find your textbook, and turn to the page that describes the Bessel function. Look for the page that has the table of Bessel functions. You'll see that the author has made a determination on what is significant and what is not significant. For example, if the modulation index is set to 2, the author would say that there's a carrier and 1, 2, 3, 4 significant sideband pairs. That doesn't mean that there aren't more sidebands, it just means that they're not significant. Once again, this is on a dB scale. So if you talked about a signal that was 80 dB down, which is basically this point here, you might say that this is not significant. You might say this is not significant. At some point, these signals would be below what we call the noise floor, and at that point, they're just not worth talking about anymore. Speaking of noise, hold that thought because we're going to come back to it in a week or so. Now that we know a little more about Bessel functions, we can come back to this graph and determine what the amplitudes are. First, let's make an assumption. Let's assume the modulation index is equal to 1.0. Consulting the table, that would tell us that there are 3 significant sideband pairs. The carrier would be at 0.77 or 77% of its original voltage. The first sideband pair would be at 0.44. The second sideband pair would be at 0.11. And that third sideband pair would be at 0.02. Since there are only 3 sideband pairs, let's come back, erase this, and enter 3 for n, where n is sideband pairs, giving us a bandwidth of 300 times 2, which is 600 hertz. Our final topic for today is directly related to the bandwidth of FM transmissions. It's known as Carson's rule, which states the bandwidth is 2 by the maximum frequency deviation plus the maximum modulating frequency. Somewhere in these notes, we wrote that a system had a frequency deviation of 12 kilohertz and a maximum modulating frequency of 4 kilohertz. Carson's law would tell us that the bandwidth is 2 by 12 plus 4 kilohertz for a total bandwidth of 32 kilohertz. Let's finish this discussion by sketching the spectrum based on these numbers and see if things make sense. There will be a carrier. The first sideband pair would be at frequency carrier plus 4 kilohertz and frequency of the carrier minus 4 kilohertz. From there, it would be frequency of the carrier plus 8 kilohertz. Then it would be plus 12, and finally plus 16, giving a total bandwidth of 32 kilohertz. That's it, folks. We have 2 ways to estimate the bandwidth of an FM transmission. The first, we can say that the bandwidth is equal to 2 by the maximum modulating frequency by n, where n is the number of significant sidebands. And then we had Carson's rule, which told us that the bandwidth is 2 by the frequency deviation. We want to specify the maximum frequency deviation plus the modulating frequency. Of the 2 methods, you'll find that Carson's rule generally has a lower estimate. Perhaps you noticed that in this particular example, because if you consult your textbook and you look at the number of significant sideband pairs, you'll see that for a modulation index of 3, there should be 1, 2, 3, 4, 5, 6 pairs, not the 4 pairs as suggested by Carson's rule.